Welcome back, Trailblazers, to another deep dive into the source material right here on the Digital Pathology Podcast.
Hey everyone, great to be here.
So today is April 1st, 2026, and we've got a really fascinating matchup to look at. We are essentially looking at a humans versus machines showdown.
Yeah, but with, actual life or death stakes in diagnostic medicine, it's not just a game.
Exactly.
Yeah.
Our mission for today's deep dive is to explore a brand new paper that just dropped last month, so March 2026, in the journal Biomedicines.
Right, which is published by MDPI.
Yep. And this research comes to us from a team at Karadeniz Technical University in Turkey. The authors are Teoman, Turkmen Usta, Sagnak Yilmaz, and Ersoz.
And the paper is titled, let me make sure I get this exactly right, Ki-67 Proliferation Index in Pulmonary Neuroendocrine Neoplasms.
Which is a mouthful, but the hook here is just incredible. They pitted 4 human expert pathologists against 2 distinct AI systems to count tumor cells.
To see who wins, basically. And more importantly, to figure out if AI can safely standardize how we grade these specific, notoriously difficult lung tumors.
Because right now, that is a huge bottleneck, isn't it?
Oh, absolutely. I mean, we often project this aura of, absolute mathematical certainty onto diagnostic medicine. We want to believe that classifying a tumor is just this strictly binary exercise.
Right, you either have it or you don't.
Exactly. But the reality of a pathology lab is incredibly tactile, and quite frankly, it's visually exhausting. The foundation of patient care frequently rests on someone just staring through a microscope.
Doing a painstaking subjective manual count of cells, right?
Yes, without succumbing to sheer visual fatigue. It's really hard work.
And that tension between the limitations of the human eye and the clinical demand for mathematical precision is exactly what we're unpacking today. So before we look at the AI showdown itself, we should probably establish why this specific medical problem needs solving.
Yeah, let's talk about the subject matter. Pulmonary Neuroendocrine Neoplasms, or PNENs.
Right. For the Trailblazers listening, you probably know they're a highly heterogeneous group of lung tumors.
Highly. I mean, they run the absolute gamut. On one end, you have typical carcinoids, or TCs, which are usually pretty slow-growing and indolent.
But then on the other end, you've got large-cell neuroendocrine carcinomas, the LCNECs, which are highly aggressive.
Exactly. Very poor survival outcomes there. But sitting right in the middle is the atypical carcinoid.
The tricky one.
Very tricky. It's this notoriously difficult diagnostic gray zone. And accurately classifying where a patient's tumor falls on that spectrum dictates everything.
The therapy, the prognosis, everything.
Right. So you need an objective tiebreaker to figure out exactly how fast that tumor is growing.
Okay, let's unpack this for a second. Think of the Ki-67 protein like a neon sign flashing under construction inside a cell.
Ooh, I like that.
The more of those neon signs you see, the faster the tumor is dividing and growing. That's our biomarker here, the Ki-67 Proliferation Index.
Yeah, and what's fascinating here is, even though Ki-67 isn't formally incorporated into the current WHO grading system for lung neuroendocrine tumors just yet, it's widely used anyway.
You kind of have to, right?
Exactly. It's the de facto standard in routine practice. Pathologists use it as an essential adjunct marker, especially for those borderline cases where the morphology alone just isn't giving you an answer.
But this is where we hit that human bottleneck you mentioned earlier. Because getting that Ki-67 index manually is, well, it's agonizing.
It really is. You're asking a highly trained physician to manually count hundreds, sometimes thousands, of cells. And first you have the interobserver variability of just picking the hot spot.
The hot spot being the most active, dense area of the tumor.
Right. Pathologist A might look at a slide and think the top left corner is the hot spot. But pathologist B might think, actually the bottom right looks slightly more active.
So they're not even counting the same cells to begin with.
Exactly. And beyond just finding the hot spot, you have the cognitive load of the count itself. You have to differentiate an actual tumor cell from, like, a reactive lymphocyte or a stromal cell.
And then decide what actually counts as a positive stain.
Right, because biology isn't perfectly binary. You use a DAB chromogen, which creates a brown stain in positive nuclei, while negative ones are blue. But you frequently get these pale brown blushes.
So you're constantly second-guessing. Like, is that weak background noise, or is that a true, weak, positive signal?
Exactly. And if you're sitting in a lab right now listening to this, you know exactly how exhausting it is to constantly calibrate that threshold in your head all day long.
It's no wonder pathologists disagree on these counts, especially in those atypical carcinoids where just a few percentage points changes the entire diagnosis.
Exactly.
So Knowing how variable manual counting is, how did Teoman and her team design a fair fight between the humans and the machines?
Well, they started with a highly curated dataset. They pulled 63 retrospective cases of PNNs from between 2020 and 2025.
Okay, 63 cases.
Yep. 29 typical carcinoids, 13 atypical carcinoids, and 21 large cell neuroendocrine carcinomas.
I noticed they excluded small cell lung carcinomas entirely from this study.
They did, yeah.
From a digital pathology perspective, that actually makes total sense because small cell carcinomas are almost always diagnosed on tiny needle core biopsies, right?
Right, or cytology specimens. And for this kind of robust image analysis, you really need the massive real estate that you get from surgical resection.
Yeah, a tiny needle biopsy just doesn't give the algorithm or the human enough tissue architecture to reliably hunt for a true hotspot.
You're just looking at a fragmented sample. So by sticking to surgical resections, they ensured they had enough whole slide context.
Okay, so they have these 63 cases. What were the actual rules of the game?
So 4 highly experienced pathologists were tasked with independently evaluating the Ki-67 index. They had to manually count about 2,000 tumor cells per case.
2,000, wow.
Yeah, it's a lot. And they were totally blinded. Blinded to each other's results, blinded to the AI, and blinded to the clinical data.
But there was a catch, right?
A brilliant catch. Crucially, they were all looking at the exact same predefined hotspot.
A senior pathologist actually went in and digitally annotated the exact region for every single case before they started.
Yep. All 4 humans and both AI systems were forced to look at the exact same pre-drawn box.
Okay, here's where it gets really interesting.
Yeah.
I have to ask, if you're designing a study to test real-world variability, and you know the biggest problem is humans picking different hotspots.
Yeah.
Why did the researchers predefine the hotspot for them? Doesn't that artificially inflate how well the humans perform?
It does, but they did it to isolate the counting variable. Think about it. If you let everyone pick their own hotspots and the final percentages don't match, you have no idea why they didn't match.
Oh, I see.
Was the AI terrible at recognizing a tumor cell, or was it just analyzing a completely different geographic region than the human?
So you have to separate the task of finding the hotspot from the task of actually counting the cells.
Exactly. By predefining the hotspot, they brilliantly isolated the counting variable. They needed to prove whether the AI could actually classify cells as accurately as humans in a controlled environment.
Eliminating the location choice altogether. That makes perfect sense. So with the arena set, let's look at the results. How did the humans do?
Staggeringly well. Because the task was purely counting inside that pre-drawn box, the 4 pathologists had near-perfect agreement.
The study reports an intraclass correlation coefficient, or ICC, of 0.998.
Right. And for context, an ICC of 1.0 represents absolute mathematical perfection. So 0.998 is just a stunning level of concordance.
It's basically flawless.
It proves that when you remove the ambiguity of finding the hotspot, human experts are incredibly consistent at categorizing these cells.
Although there was a slight dip when you look at the atypical carcinoids, right?
Yeah, good catch. The agreement across the board was great, but for those tricky atypical cases, the ICC dipped to 0.840.
Which makes sense, because that's that exact diagnostic gray zone we talked about.
Right. Those tumors have heterogeneous staining patterns. Even looking at the exact same 2,000 cells, humans still experience a little friction deciding if a pale cell is positive or negative.
Okay, so the humans brought a near-perfect 0.998 to the table. Let's introduce the AI competitors.
They use 2 distinct commercially available digital pathology systems.
First up was the Roche UpPath Ki-67 algorithm, which analyzed slides scanned on a Ventana DP600 scanner.
And against it, they ran the Verasoft VeraSight Ki-67 algorithm using slides digitized on a Leica Aperio AT2 scanner.
Now, the paper has some really vivid imagery explaining how these 2 algorithms actually see the tissue.
Yeah, they operate quite differently when you look under the hood.
From what I read, the Roche system operates almost like a simple binary on-off switch.
Exactly. It segments the nuclei and basically just drops a yellow dot on any nucleus it thinks is positive and a black dot on the negative ones. Hard binary.
Right, but the Verasoft algorithm operates more like a dimmer switch.
Yeah, it grades the intensity of the stain. So it uses red dots for a strong positive, orange for moderate, yellow for weak, and blue for negative.
That's fascinating. So how did they stack up against the humans?
Both AIs correlated incredibly well with the human experts. The Roche algorithm hit a Spearman correlation of 0.961,
Wow.
and Virasoft hit 4904. Plus, the two AIs even agreed with each other at a rate of 0.926.
So they're all basically arriving at the exact same clinical truth.
Exactly. Whether a tumor had a proliferation index of like less than 1% or a massive 85%, the algorithms tracked right alongside the human consensus.
Okay, but I have to push back here for a second.
Sure.
If the humans are already scoring a near-perfect 0.998 on their own, why do we even need the AI at all? It seems like an expensive solution to a problem that doesn't exist.
If we connect this to the bigger picture,
Yeah,
you have to remember why the humans scored a 0.998 in this study.
because the hotspot was predefined.
Yes. A senior pathologist had already done the grueling work of finding the hotspot and standardizing that 2,000 cell boundary for them.
And in a busy clinical workflow, nobody has time to do that for every single case.
Exactly. Pathologists simply don't have the time to meticulously hand count 2,000 individual cells to achieve that perfection every time. They're often forced to sort of eyeball it.
Which brings all that interobserver variability rushing right back in.
Right. So the AI isn't necessarily smarter than the human, but it provides that exact, meticulous level of precision instantly.
Without getting eye strain.
Right, without fatigue. It standardizes care across different hospitals every single time.
Okay, that makes sense. But knowing the AI can count accurately is one thing. The real question is, does it actually translate to meaningful clinical diagnoses?
The so what of the study?
Exactly. Does it help the oncologist waiting for the pathology report?
Well, to answer that, the researchers translated those raw percentages into 3 actionable clinical tiers.
Right, I have those here. A low index is 0 to under 10%. An intermediate index is 10 to 25%. And high is anything over 25%.
And the data stratified these tumors beautifully into those exact buckets.
It really did. The typical carcinoid stayed strictly in the low bucket, with a median of just 2.09%.
Barely ticking over.
Right. Then the atypical carcinoid sat perfectly in the intermediate bucket, with a median of 16.2%.
And those highly aggressive, large-cell neuroendocrine carcinomas just rocketed into the high bucket.
A median of 63.7% for those. So what does this all mean for our trailblazers listening today?
It means the categorical agreement between manual scoring and AI scoring was excellent. They used Cohen's kappa to measure it.
And Roche hit a kappa of 0.877, while Virasoft hit 0.827.
Right, and anything over 0.80 is considered almost perfect agreement. So it proves AI isn't just generating accurate math.
It's generating reliable clinical interpretations.
Exactly. It can tell a doctor exactly how aggressive a patient's tumor is, just as effectively as an expert human.
That's incredible. So just to recap our journey today, we went from the biology of PNENs to a perfectly controlled counting showdown.
Yep, isolating the counting variable.
And proved that AI can definitively match the microscopic precision of an expert pathologist without the visual fatigue.
It's a phenomenal validation of the tech, but, this raises an important question.
Oh.
Yeah. In this study, the AI proved it can flawlessly count the cells inside a predefined hotspot selected by a human. But as these digital pathology systems evolve, the next frontier isn't just counting.
It's hunting.
Exactly. What happens to the diagnostic workflow when the AI is tasked with autonomously scouring the entire slide to discover the most dangerous hotspot all on its own?
Man, that is a provocative final thought. When the machine stops waiting for us to draw the box and just starts drawing the box itself.
It's a whole different ballgame.
Well, thank you, Trailblazers, for joining us on this Journal Club deep dive into the source material. We hope this exploration gives you something to mull over the next time you're evaluating a digital workflow for your lab.
Or staring down a tricky Ki-67 stain.
Exactly. Think about how AI might soon be acting as a digital second opinion in your own clinics. Keep pushing the boundaries, and we will catch you on the next deep dive into the source material.